Hey folks, we're back, chapter 3. Hell yeah. Let's get this started. Chemical bonding. Chemical bonding refers to methods by which compounds are held together. Two basic types of bonding. I'll learn to speak in a second. Promise. Ionic bonds, covalent bonds. No matter which type of bonding occurs, it's a result of the combining elements attempting to reach a stable state or a stable electronic configuration under the conditions that exist at that time. Each element, we've seen in the previous chapter, has a given number of electrons. And those electrons in the outer shell, the valence electrons, are going to determine kind of, quote unquote, the stability here. That's where it comes into play. Valence electrons, the electrons in the outermost shell only, are involved in the bonding between the atoms. How well element B's electrons are held on by the atom may determine the type of bond that occurs. The attraction between the nucleus of the atom and the valence electrons for the given atom is called the electronegativity. Definition right there, note carded. Elements whose atoms have a relatively high electronegativity will tend to hold on to their valence electrons and will even pull electrons from other elements whose electronegativity value is less. So if I have a high number, I'm relatively powerful, I'm relatively stable, and I'm going to draw to me stuff from the other side if it's weaker than me. When two elements whose electronegativity values are similar, they will generally share, or it says atoms of the same element, okay? So if I'm similar, I will more than likely share, whereas if I am larger and the other one's smaller, I will likely pull away and steal. I'll just rip it right out. Ionic bonds are those that are held together by the attraction of the opposite charges of the combining atoms due to a transfer of electrons that can also be known as electrovalent bonds, okay? Ionic bonds form when one element that has a great attraction for its valence electrons tends to gain electrons, okay? It's an increase in negative charges, and another element is less, tends to lose some or all of its outer electrons, causing it to become positive. Remember, these things are electrically neutral. So if I have a large element, a large atom of an element with a high electronegativity number, I am going to rip one or more electrons from somebody else. This increase in electrons now turns that molecule negative. It acquired more negative particles, it becomes negative. And the one that did the losing went from a neutral charge of 0 to positive, because now the protons in the nucleus are higher in number than the electrons in the shells. And this is how ionic compounds are held together. Ionic bonds are the result of the opposite attraction between ions of opposite charges. Ion is an atom that has either lost or gained electrons and so now has a charge. Atoms in their natural state have the same number of electrons as protons. We've beaten that to death, okay? If these are the same, then the atoms are neutral. Then when we start playing and grabbing and pulling side to side, things start to change. Two types of ions, cations and anions, right? Cations and anions. And I know it says items. Remember in chapter 2 I said I use a voice recognition thing to dictate lessons, and that's what happened here. Cations, positive, okay? Cations, cathode, positive. Cations are those ions that have a positive charge. It's a result of the loss of electron. It's neutral. I lose the negative stuff. I become positive. Sounds like my last several relationships. They're named cations because they were the types of particles attracted to the negative electrode, okay, in a solution with a current passing through it. Anions are ions that have a negative charge. The negative charge due to the atoms having gained electrons. They are named anions because they were attracted to the positive electrode anode in a solution with a current passing through it. Monatomic ion is an ion composed of only one atom of an element, whereas a polyatomic ion is an ion composed of atoms of two or more elements, and these are known as radicals. Definitions. Note card. And these are the ones you should own. Ammonium, arsenate, bicarbonate, borate, carbonate, cyanide, hydroxide, hypochlorite, nitrate, nitrate, sulfate, sulfite, phosphate, phosphite, tetraborate. Own them. Note card them. Regurgitate them until you see them in your sleep. Polyatomic ions will always have a charge associated with their formula when not written as part of a compound. So if we're writing NaCl and it's not part of a compound, okay, we should be showing what their charges are. When they're written as part of a compound, the charges are omitted because in a compound, it's zero again. Let that sink in for a second. If I'm just writing NaCl and I want to know what the charges are, it's not part of a compound, it's sodium and it's chloride. Which one is positive, which one's negative? But the instant I create the compound sodium chloride, I have a zero. I have a neutral because it's a stable compound by this point. The positive of the sodium, the negative of the chloride are going to cancel each other out. So even though the individual atoms have a positive and negative, when they combine together into the compound, they turn into a zero. It's only when they are separate, and I want to list them separate so I can see who has a positive, who has a negative, that I worry about this. Many individual elements may also exist as ions when placed in a solution. The most common are those found in the following groups of the periodic table: 1, 2, 3, and 7. Okay, 1, 2, 3, and 7. Groups 1, 2, and 3 will always tend to lose their valence electrons. So you can see that they generally have positives. Now you see a couple of exceptions there in the middle. Hey, it is what it is. But 1, 2, and 3 always tend to lose. Elements in group 7 may either gain or lose electrons, but they tend frequently to gain them, which causes them to have a negative charge. Okay? An ionic compound is then considered to be a compound whose atoms are held together by the opposite charges of its ions. It seems so complicated. Some of you are having a meltdown right now. Hey, end of the day. One's positive, one's negative, and they stay together because opposites attract. Plain and simple. That's what's happening here. With covalent bonds, they're held together by sharing. Okay? They rely on the atoms, the other's atoms, to provide the appropriate number of electrons to reach the stable electronic configuration. Instead of ripping them apart, they come together, they start sharing the electrons, and life is good. There are several types of covalent bonds based on the number of electrons that are shared. This is so hard. A single bond, oh my God, they share one pair of electrons. Notice we're talking about pairs, okay? One shares one, the other one shares one. So what happens in pairs? If it's a double bond, double covalent bond, 4 electrons, 2 pairs, 3 pairs. Okay, you should be getting this right now. This should not be hard. A special type of single covalent bond is called a polar bond. That's going to get asked. In a polar bond, there is an unequal sharing of electrons between the atoms that causes a situation in which partial charges appear. This is quite common in the case of hydrogen bonding to other elements. This particular situation occurs when the water molecule forms H2O. The hydrogen to oxygen bonds cause the hydrogen atoms to take on a partial positive 1 and the oxygen to take on a partial negative 2. The two polar bonds are then called a dipole or a dipolar bond. So, polar bond. Don't think of the Coca-Cola polar bear. Think positive, negative. Electro. They're sharing, but instead of just being a perfect sharing, it causes a little bit of a change in positive and negative. So a polar bond would be sharing that also kind of results in this little change like an ion. This, how you can meld it together, how you can kind of keep it straight in your head. The valence of an element, or oxidation number, refers to the number of electrons that are lost, gained, or shared when an atom of an element combines. Sometimes the valence refers to the combining capacity of the element. Okay? So now we've seen valence electrons, which are the electrons in the outermost shell, but the valence of an element refers to the total number of electrons that are lost, gained, or shared. Not just the total number in the shell, don't confuse that. The valence is the ones that are actively gained, lost, or shared. Valence is referred to as the combining capacity of the element. Found this cool chart. Okay, I found this cool chart. You can go ahead and, pull it up on the extranet if you want to. To be able to use the valence or oxidation state of an element, there are some rules for determining the numbers. The sum of the oxidation numbers of all the atoms in a compound is equal to 0. Remember, once you form a compound, it should be neutral, should be stable. The sum of the oxidation numbers of all the atoms in a radical or polyatomic ion is equal to the charge on the radical or polyatomic ion. So it then gives you the rules. Okay? Then gives you the rules. Memorize them. Okay? Memorize them. It gives you a little bit of a problem here. Okay? So it starts with solve for the valence or oxidation number of nitrogen in the formula N2O3. So first thing, list the element's number of atoms. I have 2 atoms of nitrogen, 3 atoms of oxygen. And I multiply that by an oxidation number. Well, in this case, I know that oxygen is -2, but I don't quite know what's going on with nitrogen. So they just write that into a formula. Okay? This is pretty much basic algebra. Grab my handy dandy little digital pen here. So I basically have 2x plus -6 equals 0. Well, I'm solving for x. The first thing I'm going to do is 2x equals 6, because to get rid of the negative, I got to do this positive thing. Oh my God, it's math. I'm bursting into flame. I'm a musician. I don't do math. Well, your instructor's a musician that's doing math. Then I got to get rid of the 2. Since I got to equal 0, x equals 3. Well, 2 times 3 minus 6, because it's a negative, equals 0. 6 minus 6 equals 0. I'd hope so. Unless you work for the federal government, and then who knows what the hell it is, because government has its own word math. It's not crazy. But it does require you to just simply solve for x. And you have to be given 3 variables, or it's just not going to work. You might have to distinguish how those variables have been given to you. It might just be like, your oxidation number is this. Okay? You might have to do a little bit of memorization here. Some elements, such as those found in certain groups, group 4 through group 7, and the transition elements have the potential to have more than one oxidation state, valence or oxidation number. And these elements are said to be multivalent. Okay? They can share, gain, or lose in more than one way. That's because their electronegativity values and the number of valence electrons allows for the possibility of combining with elements in which they might gain in one case and lose with another. Plain and simple. I can do different things. So multitask, multivalent. When naming inorganic compounds, certain rules apply for naming the compounds. Ionic compounds are named differently from covalent compounds. We're learning a language. Chemistry is a language. And when you say something, chemists can think of it and understand what you're talking about and where it comes from. Some inorganic compounds can be named after their crystalline form as well as their acid or base name. And there's some basic principles to remember when naming inorganic compounds. Now, I'm not going to go over each and every one of the examples in the book. That's why it's there. Read the book, and these are fairly self-explanatory. This is not like, quantum physics here. If you have a monatomic ion that has a lower oxidation state, the suffix is OUS. If it's a higher oxidation state, it's IC. Basic rule. If you have a polyatomic ion with a lower oxidation state, the suffix is ITE. If it's a higher one, ATE. So memorize one, own it cold, and you should be able to figure out the opposite. When naming the ionic compounds, give the name of the cation first, followed by the stem of the anion plus the suffix IDE. The number of atoms in an ionic compound are never given in its name. If the ionic compound is composed of one or more polyatomic ions, you should name the cation first, by name if it's a radical, followed by the stem of the anion plus the suffix IDE. If the anion is a radical, simply just give its name. These are basic rules. Okay? I am 99% more likely to ask you about a rule than an application of the rule, because I know this stuff gets confusing, and many of you, like myself, are not chemists. So I'm not going to beat you to death. But if I ask you a true and false, based on something like this, you should be able to answer it. When naming covalent compounds, you generally name the elements in the order they appear, giving the number of atoms for each element as a prefix to its name. So with covalence, we have to give the number of atoms. Okay, we have to give the number of atoms. The last element's name is abbreviated using its stem, followed by the suffix IDE. If only one atom of the first element is present, the initial prefix mono is omitted. It's understood to be 1. Be sure to review the partial list of inorganic compounds listed on the next 3 pages, and notice that the prefix mono is only omitted on the first element in a covalent compound. I am 100% more likely to ask you the name of a compound, okay, that is in the book. 100%. If it's on these 3 pages, it says, this is the name, here's your line formula, here's your name, I most certainly will probably ask you questions like that. So folks, thank you for attention, and we will see you in the next lecture.